Hello, everybody. How are you? I wonder if you can hear me at this point. I'm Po Shen Lo. Welcome to our live stream. I'm just going to pause for a second because sometimes it takes a little bit of time to connect. I apologize. I can't actually join too much of this today, but I just want to welcome you to our channel because we are absolutely thrilled to be working again with Math Kangaroo. I was actually just having dinner with a bunch of parents from this area where I'm in, which is outside of Boston, Massachusetts. And parents that I was talking to also thought that Math Kangaroo was excellent, a really, really excellent source of clever problems that aren't just based on remembering some formulas. Well, what we'd like to do next is we're always lucky to have somebody from official Math Kangaroo present Math Kangaroo. So I just want to introduce, we have Anna Yelon, and she's a dedicated wife, mother, small business owner, and a passionate community leader with multiple postgraduate degrees, including an MBA, a master's in geophysics, and a PhD in finance. With over a decade of experience as a senior financial advisor, she refined her expertise in risk assessment, budgeting, forecasting, and business longevity, all really useful things. But she's also interested in advancing math education. So she founded her own math academy and serves as the Texas State Director of Math Kangaroo USA. Besides that, she's also deeply involved in civic and community service. She's the vice chair of Leander Wins, and she holds commissioner roles in several key committees. Well, I'd just like to invite Anna to say a few words to welcome, representing Math Kangaroo, and then we'll bounce back to our team.
Hi, hello everyone. My name is Anna Yelon, and good evening from Texas. So I'm thrilled to welcome all of you tonight. Thank you to being part of Math Kangaroo community. It's wondering and wonderful to see you many of you here in our competition, Math Kangaroo. We are excited to share what other 53,000 students from all 50 US states participated in the 2025 Math Kangaroo competition. And we would love to say thank you for all of you, for students, for parents, volunteers, educators, managers, directors, all of you. And we have a couple of few important updates for you. So answer case is already on our website, and results will be available in parents' account by May 1st. It's actually my birthday also. So also the grades from 1 to 3, so first, second, and third, will be April 29th, grades are 4, 5th, and 6th, April 30th, and grades from 7 until 12, May 1st. Students can review the exams in their test accounts beginning May 1st. So also, we would love to invite students for grades 1 through 8 to our Math Kangaroo online summer camp, and you still can use our code LESS50 to save $50 off for your registration fee until end of April. So again, we are very thankful for all of you. And so check your result and please keep going. And we would love to invite you guys for our next competition, 2026. And from my notes, I very love Math Kangaroo because it helps students discover how fun and rewarding math can be. When you enjoy our Math Kangaroo, you build confidence, creativity, and lifelong love for problem solving. So thank you again for being here, and let's keep celebrating math together.
Well, thank you so much for representing Math Kangaroo, Anna. It's a pleasure to have you here. And so I think it's maybe poetic that I happen to be probably only about 10 miles from Corey right now. And well, Anna, you're in Texas, which is also where Gloria's from. In fact, those are the two incredible stars who are going to be leading this entire show. Corey and Gloria, why don't you take it off from here?
Hello,
Hello, I'm Gloria.
my name is Corey.
And right before we dive into the fun, exciting math we have prepared for all of y'all today, we're going to go ahead and do some quick introductions so you guys kind of know who we are. So I'm going to introduce Corey. So Corey is a senior at Lexington High School. He's been involved in math competitions since middle school actually, such as the Amy and USAMO. He also loves teaching people and being able to help others. And besides math, he also enjoys spending time outside and playing different sports. So hey Corey.
Hi guys, my name is Corey, and today I'll be teaching with Gloria. So Gloria has qualified for the Amy and attended the Texas Math Count State competition since 7th grade. She was a third best speaker and an octo finalist at the 2023 National Middle School Tournament of Champions in Lincoln Douglas. In her free time, she is an avid reader who likes to write poetry and listen to K-pop. So say hello to Gloria.
Hey guys, super excited to be here. So hey Corey, we're here for math, so why don't we just dive in?
Yeah, sounds great. Do you want to start us off on the first question?
Yeah, so the first question we have prepared for y'all tonight is how many of the following four numbers, 2, 20, 202, and 2020 are prime? So first off, let's just list the two numbers out. We have 2, 20, and 202 and 2020. And so, just for quick clarification, prime numbers are numbers that don't have any factors aside from 1 and itself. So there's a really quick way to solve this problem, and it's just by looking to see if they have more than two factors. And I already see the chat is bursting with answers, which is super duper awesome. And so we're going to go ahead and just quickly solve this, right? So, well, 2020 is even. That means it has to divide by 2. So therefore, 2020 cannot be a prime number. And on that same kind of reasoning, well, 2000 or 202 is also even. It's divisible by 2. It's not an option for being a prime. And then 20, well, it's also divisible by 2. So that can't be a prime either. But wait, Corey, what about 2? 2 is divisible by 2, so therefore it can't be a prime either, right?
Well, actually, 2 is the only exception to this rule because 2 is actually, we say that all the even numbers aren't prime because they can be divided by 2, but 2 is itself, so it actually counts as the only even prime.
Wow, wait, that's super interesting. And since Corey has just awesomely told us that 2 is the only even prime, we can go ahead and confidently say that the answer will be B or 1, as so many of you guys have been saying in chat. Okay, so we'll go ahead and take a quick look at the answer, and voila, it is B. Okay, wait, this question was super fun, Corey. What's the next question?
Yeah, well, let's take a look. Well, this question was pretty good. Let's look at the next one. Question number 3. So Miguel solves 6 Olympiad questions every day, and Lazaro solves 4 Olympiad questions every day. How many days does it take Lazaro to solve the same number of problems as Miguel solves in 4 days? Okay, so let's see. So this is a very, very wordy question right here. But let's write the key information down on a new slide. So if we read here, let's see. Is everything working fine? I think it is. Great. We have Miguel solving 4 days of questions, right? So, oops. Let's see. We work for M was gonna work for 4 days, like that. But we want to know, okay, I'm working for 4 days. How many questions am I gonna solve? We need to know how fast Miguel is. And it says Miguel solves in 4 days. Well, Miguel solves 6 questions per day, right? It says here that Miguel solves 6 Olympiad problems every day. So if Miguel solves 4 days worth of questions and he does 6 per day, how many total questions is Miguel going to solve? Let's see. Oh, people are saying they can't see the problem. Let me make this a little bigger, actually. Here, can you guys see this? 24, okay. So hopefully you guys can see this. And I see that Sanskriti has said that, yes, Miguel solves 24 problems. So he solves a total of 24 questions. And now this is how many problems that we need Lazaro to also solve, right? Now, Lazaro solves 4 per day. So we know that L solves 4 per day. But we don't know how many days he has to work for. But we know that we have to end up with the same end result of 24 total questions. So how many days do I have to work of 4 questions per day to solve 24? Let's see if chat knows this. Here, Gloria, do you know this?
Let's see. Miguel takes 4 days to solve problems with 6 problems per day. So if he solves 6 problems per day with 4 days total, I see a lot of you guys have put it in chat. Quick shout out to everyone. We can just do some quick multiplication, right? So we do 4 times 6, and just quickly multiplying that out gives us 24. So Miguel does a total of 24 problems. Okay, this is awesome. But wait, Corey, why is that information important? I completely forgot. Why do we need it?
Well, we know that they have to solve the same total number of questions. And it looks like we're having some technical difficulties because not the right slide is showing up. On here. I think it's glitching out a little bit. So hopefully you guys have enough information on this slide right here to know that I saw a bunch of you guys already typed it in chat that because we know that they have to solve 24 questions, they must be working for, Lazaro must be working for 6 days. Right here. 6 days. So the answer should be answer choice C, which is 6. And maybe you guys can't see it on my screen, but Gloria, if you could talk a little bit, you can see it on Gloria's screen.
Yeah. So remember, 24 problems total. That's the amount of problems Miguel did. And then we just divide by the number of days Lazaro took to solve the problems, right? So 24 over 4 gives us 6 days, our answer choice of C. So hopefully everyone can see my screen. And okay, yeah, it looks like everyone can see my screen. This is super duper awesome. Okay, so moving on, the answer is indeed C. So I see we got the correct answer. Okay. Awesome. All right, on to problem number 5. So a large square is divided into smaller squares. In one of the squares, a diagonal is also drawn. What fraction of the large square is shaded? Oh, okay. So now it looks like I think the shading, it looks good on my screen. Okay, that's good. So you guys can all see it. Awesome. All right. So it looks like it looks kind of tough, right? Because we don't have any side lengths. So what are we supposed to do? But I see a lot of you guys have been putting some things in chat, some numbers. So in the case of like a problem where we aren't given numbers, something that we can quickly do is we can just kind of assign numbers here. So
this one gives a question.
if we just say, like, for example, this small side length over here is 1, right? If we say that it's 1, then the total side length of the square is 2. And so just by assigning some numbers, right, it just helps us, it just makes calculations much easier. And you can also use variables, but I prefer using like actual numbers. And so this time, instead of just going ahead and just directly, finding out the areas, what I'm going to do is I'm going to cut this into chunks. I'm going to find the area of this square, then this square, this triangle. Oh, wait, you can't see my hand. This triangle, and then this bottom square. So this bottom square, since it has a side length of 1, I'm going to do 1 times 1 to give us 1 for the area of the bottom square. And then 1 times 1 for the triangle. But wait, because it's the triangle, right, we need to divide by 2. Because the triangle area formula is base times height divided by 2. So 1 times 1 over 2 to give us 1 over 2. Now, you might be asking, what about these 2 small squares? What about their side lengths? Well, since they're squares, right, their side lengths have to all be the same. And so this means that the side length of both of the squares are just going to be 1 over 2, or a simple 1/2. Awesome. So this is super duper awesome. We know the side length of one of the small squares. That means the area of one of the small squares must be 1 over 2 times 1 over 2, or 1 over 4. Okay, so we have 1 over 4 here. Well, we know that these two small squares are identical. They're exactly identical. So we can go ahead and put 1/4 down as the area for the other small square as well. And so now we can just quickly sum up the area, our shaded area, right? We do this by doing 1/4 plus 1/4 plus 1/2 plus 1. 1/4 plus 1/4 just gives us 1/2. And 1/2 plus 1/2 is 1. So these three fractions over here just consolidate into 1. And so our equation becomes 1 plus 1 becomes 2. But wait, we're not done yet, right? This is the area of the shaded region. But the question is asking what fraction of the large square is shaded. So we're going to take to the area of our shaded region, and we're going to quickly look. Well, the area of the square, right, or the side length of the square, we already said was going to be 2. This means that the area of the big square is going to be 2 squared, or simply 4. And so therefore, the fraction of the large square that is shaded is equal to 2/4, which means it is equal to 1/2. And thus our answer choice is E, as so many of you guys have been putting in chat. So super duper awesome. All right.
Alrighty, guys. Just testing. Can you guys see this question? I want to see if people in chat know this. Yes, great. Stephanie, thank you. So it looks like you guys can see this question and see, test some drawing. Yeah, that drawing works too. Great. So let's move on to this question here. It says, the diagram shows a shape made up of 26 identical small triangles. What is the smallest number of such triangles that can be added to the shape to turn it into a hexagon? Great. And it looks like everybody can see this. Let's see. Alrighty here. So we want to have this sort of spiky ball shape and turn it into a hexagon. Now let's try and see if we can make a new slide here. Okay, that looks like it's working. And let's see. Let me copy this earlier diagram down. You guys see this? Oh, perfect, it works. Great. So now we have a copy of a new, fresh diagram, and we want to turn this shape into a hexagon. Now, we're only, the question says that we're only, looks like there's a lot of answers in chat already, but the question says we're trying to add little triangles here. So we got to remember, okay, we're adding triangles. Well, a hexagon doesn't have this gap in the middle right here. So it makes sense for us to try and fill that guy up. And we can fill them up on all of these different sides here. Fill up these little gaps because the hexagon never goes, like it never has a point where it just suddenly caves inside of itself, right? So again, if we look over here, there's also a problem right around here because the hexagon never caves in. So it makes sense for us to keep adding triangles to like kind of fill it in, like fill in all the holes. And we're going to keep filling in holes and keep filling in holes. And then every step we're going to look back and check and see, I know this was a problem and I addressed this problem, but are there more problems? Let's see, let's keep filling in holes. And wow, now I'm done filling in these holes. But now we look and we ask ourselves, okay, is this a hexagon? Are there any more questions? And it looks like Stephanie says, no, there's no any more problems with this hexagon. And there's no problems anymore because we know we can only fill in gaps and we start filling in gaps and eventually we reach our end shape, which is a hexagon that looks like this. Great, and now we count up how many triangles we used. There's 1, 2, 3, and then there's 3 on this side, 1, 2, 3 on that side, 1, 2, 3 on this side, 1, 2, 3 on this side, 1, 2, 3 on this side, and finally 1, 2, 3 on this side. And if you add up all these triangles, we added a total of 18 triangles to get our final answer. So let's see if we can get to the slide that gives us our answer. And look, it's D, 18. And the question asks, wow, look, it looks like the answer choice is D. So great job. Yep, Stephanie says 3 times 6 is 18, and that is the answer. Great. Now, Gloria, do you want to take us on the next question?
Definitely. Now let's go on a quick road trip with a bus, guys. So the problem asks, if John goes to school by bus and walks back, he travels for 3 hours. If he goes by bus both ways, he travels for 1 hour. How long does it take him if he walks both ways? Okay, so let's just draw a quick diagram. So let's say that this is his house. This is going to be John's house, and this is going to be the school. And if he goes by bus and walks back, he travels for 3 hours. If he goes by bus both ways, he travels for 1 hour. So I'm just gonna say the distance is let's just say 1, right? The distance is 1 mile, or 1 kilometer. All right, so let's say that the bus moves at a speed B and then John walks at a speed of J. And so, well, the first case where he goes to school by bus and walks back, we're going to get the equation 1 over B plus 1 over J, right? Because distance over speed times time. And so therefore, distance over speed is going to give us time. So 1 over B plus 1 over J is equal to 3. And then 1 over B plus 1 over B, because he goes back by bus both ways, is going to be equal to 1. Okay, so we know that 1 over B and 1 over B, well, they're the exact same thing, right? So we can just change that to 1 is equal to 2B, and some quick manipulations show us that B is equal to 2. So you can say like 2 miles per hour, right? Awesome. So now that we know that B is equal to 2, let's go ahead and plug that into this equation. So I'm just going to quickly kind of clear my slide a little bit. I'll put my calculations up for B right over here. So hopefully you guys are over there. So hopefully you guys can still see it. And then I'll work on our new equation over here. So 1 over B plus 1 over J is equal to 3. Well, 1 over B is just 1 over 2 plus 1 over J is equal to 3. Now that we're left with only one variable, it's easier, right? It's easier to solve this equation. Sorry, guys. So we can subtract 1 over 2 from both sides, and we're left with 1 over J is equal to 2.5, or 5 over 2. And so if we do some cross multiplication, we get that 2 is equal to 5J, or that's a Y, 5J. And if we divide both sides by 5, we are left with J is equal to 2 over 5. Awesome. So you guys might say, oh, it's awesome. It takes us, 2 over 5 of an hour he travels at a speed of 2 over 5 miles per hour. You guys might go like, oh, that's the answer, but be careful because the units here, right? We're solving for J's speed. This isn't the amount of time it takes for John to walk to and from school. So now we need to create our own new equation. And so I'm just going to quickly, again, kind of get rid of my work here. I'll just quickly write down the values. B is equal to 2, J is equal to 2 over 5. And I'm going to get rid of the work just so there's more space. Awesome. Okay, now our equation tells us that John needs to walk back and forth, right? He needs to walk to school and he needs to walk from school. So we're going to get 1 over J plus 1 over J is equal to something. We don't know. That's what we want to solve for. And we know that 1 over J is equal to 1 over 2 over 5. Or 1 over J is equal to 1 over 2 over 5. But that is equal to 5 over 2. So what we're going to get is 1 over J plus 1 over J is equal to 5 over 2 plus 5 over 2, which gives us our final answer of 5, as so many of you guys have been putting it in there. And yeah, so quick shout out to Andrew. It does take him 5 hours in total. And Stephanie says take the reciprocals and multiply by 2 to get time there and back. Yeah, you guys are absolutely on the point. You guys absolutely got it. So the answer is D, 5 hours. And let's just quickly check it. Okay, awesome. It is D. Now, Corey, after that long walking, I think we're a little bit tired of this problem. So why don't we move to the next problem, Corey?
Yeah, sure. So it looks like the next problem is also going to be pretty cool and maybe also sort of related to walking. But I think my technical difficulties are still occurring. So do you mind covering this question too? Maybe take another longer walk of teaching, but I'll cover the next ones. Thank you.
Yeah, definitely. So it looks like we're getting ready, to prepare a marathon or like, I don't know, something, right? Because we're walking, we've walked to school. Now we're going to walk from A town to C town to B town, I think. Okay, so let's see. Let's read the question. The shortest path from A town and C town runs through B town. The 2 signposts shown are set along this path. What distance was written on the broken sign? Okay, so it looks like the path is going to be from So this is our path at the bottom, the pink one at the bottom. A-town is going to be at the left. C-town is going to be at the right. Okay, and so something we want to figure out is how long the distance is from A-town to C-town. Well, at this point, A-town, this distance is 2 kilometers. And this distance, sorry, I know my drawing skills aren't very beautiful, but I think they're enough for our purposes. And this distance is 9, right? Well, this signpost is right in the middle of the path from A to C town. So therefore, this distance the signpost is from A plus the distance the signpost is from C will give us the distance, well, between A and C. So 2 plus 9 gives us 11. So the distance between A and C must be 11 kilometers. But you may be wondering, okay, sure, we know the distance. How does that help us, right? Because it looks like it doesn't help us at all. But here's something really interesting. At here, B-town is 4 kilometers this way away from the sign. So B-town is 4 kilometers away from the sign. So I'm just draw something like this, right? This is B, and B is 4 away from the signpost. And what we're trying to figure out is we're trying to figure out this green length. How much is that? Well, if B is, it's 4 away from B town, right? Well, actually, why don't we go ahead and cut part of this off? So we're going to just look at this part, right? From here to here. We're going to ignore this signpost to A town. So the total distance from here to here, from signpost to C, is going to be 9 because it tells us on the signpost right over here. That is a very bad circle, but that's okay. So this will be 9 km. And the distance from this signpost, the pink signpost, the signpost with the pink dot on it, to C is going to be 4 kilometers, like it tells us right here. But wait, guys, I think I have something. The distance from the first signpost to C is 9. Well, that distance 9 must equal, so 9 is equal to, must be equal to the distance from the first signpost to B, which is 4, plus the distance from B to the second signpost. So I'm going to just do a question mark, plus the distance from the second signpost to C. And wait, we have our equation here. So just kind of combining like terms give us that 9 is equal to 8 plus the question mark. And so we can easily see that the question mark, or the distance from the broken sign to B town, must be equal to 1. And yeah, you guys have been saying that in chat. So super duper awesome. Quick shout out to Stephanie and Jerry for some amazing mathematics and subtraction. Awesome. Okay, so our answer is A, and we can take a look at the solution, and voila. Okay, awesome. But whoops. After that, tons of walking, I think we've walked really far. To maybe we're gonna go on some sightseeing, and maybe we can see some shapes, maybe something like pyramids. Is that right, Corey?
Yeah, that's right. So it looks like this question, we're going to be looking at pyramids. And let's see if I can shift this guy out of my face a little bit. Boom. So hopefully you guys can see this. And now we're looking at some pyramids here. And the question says, hopefully you guys can all see this. Which of the following shapes, which of the following shapes should, I think there might be a typo in the question, but it's asking what does it look like when we look at this from above? And I think because of some weird transparency issues, let me just color this in. So this line is filled with black, and then this line is also filled with black. So these two lines are big and thick black lines over here and over here. Yeah, I think there might be a typo. This might be shoes. It might be shoes, not shapes. Which of the following shapes is what you would see when the object in the diagram is viewed from above? Something like that. Or triangle shoes. Oh, there's shoes? Oh, maybe they're shoes. My bad. Okay, so a lot of you guys are saying B. And that might be right, but guys, how would we look at this? It's sort of like this geometrical like intuition, like practicing your geometry brain here. Because you gotta sort of like be able to visualize your things and see them from above. But I think it's gonna be easiest if we look at a new, let's see, we look at a new way to draw it. So we have a line over here, and a red line over here, and then there's sort of like this clear white line over here, and then this thinner line over there. And I just color coded it because it's really hard to see on the diagram. And that's what we have. This is our sort of shoe. And we want to look at this from above. We can imagine there's this just giant circle that smashes down on this shape. So we have this it is a sort of rectangle square base. So when we smash this down, these endpoints will stay the same. So we'll have this square and we'll smash it down, right? But this is still a red corner, that's still a red corner, this is still a white corner, and this is a yellow corner. But now it's like the shape got smushed down, and then we look at it from above, right? So if we smash it down, the red lines will look like this, the white line will be here, and then the yellow line will be here. And now it's smashed down, it's easier to look at it from above because we're sort of already looking at it from above, right? Now we want to look at our answers, and then you'll notice that B is going to be the right choice. I think you'll see it better on your guys' computers because the color coding is weird here. But the idea is that, wow, this geometry question is answer choice B because we'll just rotate it 90 degrees, and then it's going to end up looking like, it'll end up looking like something like this right here with red, red, white, and yellow. And that matches shape for B. And that's what the answer choice B is. And Yujua says this geometry question is cool. And I agree because this geometry question is super cool. And the idea here is about like orientations because, well, we know, for example, in this 3D shape, the red lines are next to each other. They're directly next to each other. So if we squish down, or if we view it from the top, the red lines also have to be next to each other here. So there's 4 lines. The red lines have to be next to each other, no matter how you look at it. But also, the question is, okay, now we have 2 red lines, right? Do I put the yellow line first, or do I put the white line first? And that question is sort of about like how, when you look at it, like the orientation, like the clockwise, counterclockwise, these geometrical attributes, some of them stay the same, some of them don't, depending on whether you look at it from above or from below. So that's pretty cool. And this question might be easy to some of you guys because you can just look at it and be like, wow, it looks like this. And I would agree that like, sometimes it's really easy to see these questions, but that's because you guys are practicing your sort of geometry brain here, and it makes you be able to see these shapes and be able to like rotate objects in your brain. And that's really cool. So if you guys keep practicing, it's gonna look great like that. Now, Gloria, let's see. This question is correct. Answer choice B. And now let's look at the next one. The next one, looks like more shapes. Gloria, would you like to take us through this question?
Yeah, definitely. So for those of you guys who are bummed out about, oh no, there was only one geometry question, well, there's actually more. So let's go ahead and solve this one. The question asks, Sasha's garden has a shape shown. All of the sides are either parallel or perpendicular to each other. Some of the dimensions shown are in the diagram. And what is the perimeter of Sasha's garden? Ooh, okay, so this one looks a little tough because it doesn't give us the side length of this really long length, nor the side length of these small heights over here. So what we can do is we have to rely on the existing side lengths that we know, like 3, 4, and 5. Okay, but 3 is going to be the total height of this figure, right? Oh, that is not a very straight line, but that is entirely fine. But if we look at this, right, 3 is the height, but don't these little heights over here add up to make the total height of the figure? So because all of these 3 little heights make up the total height of this figure, we can confidently say that all of these yellow pieces are going to be 3. So this side, or these 3 yellow pieces on the right, are going to be equal to 3. But what are we going to do with the horizontal lengths? Those look much harder to address, right? But say this is 4, right? Or sorry, this is 5, right? The green lengths are 5. And I can draw it like that, like this. And I just cut it off right at that point. Well, if I cut it off right at that point, well, these two horizontal green lengths, aren't they also equal to 5? They're just 5, right? So like, if you think about it, this is 5. I've just moved one of the lengths to be lower than the other. So therefore, the green lengths are also 5. And wait, hey, this makes this remaining little chunk over here a rectangle, right? And if it's a rectangle, that means that this pink length over here, this horizontal pink length that we know for sure is a length of 4, well, this bottom horizontal pink length must also have a length of 4. So that means that because we have two pink lines with a length of 4, we can do 2 times 4, and we have 2 5s, right? Because these two green ones together make a 5, plus 2 times 5 plus 3, or 2 times 3. Because remember, the 3 segments on the right, the 3 vertical segments on the right combined together make up 3. And so we can just quickly kind of do some multiplication to get 8 plus 10 plus 6. 8 plus 6 is 14. 14 plus 10 to get 14, or yeah, 14 plus 10 to get our answer of 24, which means that the answer choice is C, as so many of you guys have been saying. And Stephanie put something really cool in chat. She said that you can slide the 4 back and forth and nothing will happen. And that's basically the principle this whole problem focuses on. It's focusing on sliding the lengths, right? Kind of like, think of it as a puzzle. You want to see if you can move some lengths around, or like kind of like draw some lines, so that kind of like with the 3, right? You can find things that have similar lengths or the same lengths. Okay, awesome job. All right, Corey, let's see. Wait, let's actually check for answers right first. And it is indeed right. Okay, awesome. Wait, Corey, is our next problem geometry too?
Yeah, Gloria, it looks like our next question is also geometry. So see if people in chat really like this one as well. So another geo question, and we look at this and we see, wow, looks like a square with a hole in it with some weird sort of like rotated over square, and there's like a hole in it and there's some rectangles. Let's read the question. So it says a large square consists of 4 identical rectangles and a small square. The area of the large square is 49 centimeters squared, and the length of the diagonal AB of one of the rectangles is 5 centimeters. So we know that this is 5 centimeters, and we know that the area is 49. What is the area of the small square? So we want to know what this square is. Great. So now we have all of our key info. We do have an extra page over here. So let's just work with this extra page. And let me just make the sizing a little bit bigger here, a little bit bigger. Great. Now, let's put this guy off to the side. Guys, when I look at this question, I think that, well, in geometry, we can sort of try and figure out everything we know about this diagram, right? Like right now, I don't know much about this diagram other than the area is 49 and I know that AB is 5. But if I want to describe this diagram, I need to know what the side lengths of these gray triangles are. For example, this length right here and this length right here. Because then if I know these two lengths, then I'll also know the length of this side and the length of this side over here, the length of this side, the length of this side over here, and all of these sides. So all of these sides will get described if I just know the sides of these two gray triangles. And it's also very nice because we know it's a right triangle and we know the hypotenuse is 5, or the length AB. So the hypotenuse is 5, and we can call these, we can do something really complicated by calling these like 2 variables, and then we can do all this like so many variables over here, and we can write down equations, and we can use Pythagorean theorem, and then we can write down the area formula. But that's too complicated, guys. When we do math, especially nice competitions like the Math Kangaroo, we want to think on our feet, and we want to be like, okay, so I'm working with triangles, and I'm working with rectangles and side lengths. I see a 5. Can you guys tell me what right triangle has an edge length of 5? What right triangle has an edge length of 5? Like what are these two sides? Exactly. So Stephanie says a 3, 4, 5 triangle. we know as very very smart math kids, we know that, oh, the 3, 4, 5 triangle shows up often in the Pythagorean triplet. Yeah, good job. A lot of you guys all see this Pythagorean triplet. And 3, 4, 5, it's so common. So let's try it out. I think this is the intended way to solve this question, which is we put a 3 here and a 4 here, and then a 3 here and a 4 here, 3, 4, 3, 4, and then we double check. So we guess, throw our hands in the air. We're like, okay, I see a 5. I'm just assuming that this is 3 and a 4, and then throw my hands in the air and I'm like, okay, it looks like this total side, the total length of this side is 7. And we know that the area is 49. So 7 squared is 49. It all checks out. That means that this is probably how the question works. It's a 3 and a 4 and a 3 and a 4. But now we need to find the area of the inside square. So what we know is I'm going to draw a cut. Boom, a cut like that. I know that here it's length 3, and here it's length 4. And down here it's length 3. Down here it's length 3, and up here it's length 4. And I know that it describes the same length of 7. But if I cut it into this part right here is 3, right? Because look, I have this side length 3, this side is length 3, and then now this middle part we can calculate as 7 minus 3, which is 1. Or we can just do 4 minus 3, whichever way like comes to you guys first. So we know that the middle length is actually the difference between the 3 and the 4, which is 1. And then the area is just 1 times 1, which is 1 squared. So the answer is going to be, let's see, A, 1 centimeters squared. Any questions? Let's see if this works. Boom, and the answer is indeed A. Great, so that was another nice geometry square question. Oh, and Gloria, it looks like you're dealing with some more squares here.
Yeah, definitely. So once again, it's kind of geometry, right? Because we have diagrams. And it looks like we have another problem. Okay, it's fun if you guys don't laugh. All right, so the problem asks or says, Irene made a city using identical wooden cubes. One of the diagrams shows the view from above the city, and the other the view from one of the sides. However, it's not known from which side the side view was taken. What is the largest number of cubes that Irene could have used? So to start off, the way we want to approach this problem is we want to think, is there a way in which we can maximize the number of cubes used, right? Cubes used. And I see this. Well, this is our tallest tower. It has 4 blocks. So I want to have, the most amount of blocks or most amount of towers with 4 in it. So I'm just going to take, I'm just going to kind of put it over here, right? Let's say this is 2 and this is 3, because this corresponds with the two block tall tower over here, and this corresponds with the 3 block tall tower over here. Well, 4 is at this position, so that means we have 2 towers, which is good, right? But let's check the other positions. Maybe there could be more towers. And if 2 is here, 3 is here, 4 is here, well, there's only 1 tower if the side view was from here. So therefore, we don't want this one, right? Because we already have an option where there are more towers that could have 4, right? And you might be wondering, wait, what if one tower has 4 and the other has 1? Well, remember, the problem says we want to maximize it, right? So all the towers in the same row or column as the 4 block tall tower, they're going to have the same length or the same height. Now let's look at it from the other side. From this here, 2 is here, 3 is here. Awesome. 4 also has 2. But you might be wondering, what makes this green and this pink one different, or the yellow one different? Well, the key thing that's different here is that there is that 1 here, right? We have 1 here. 3 here is only going to have 2 towers in the green. But with the yellow, 3 can have 3 towers. So that's one thing to consider. So we know that yellow is going to be more superior than green or pink. And so we can go ahead and finally look at the last side. The side view could have been taken. Now this time this is going to be 2 and this is going to be 3, 4, 1. Okay, awesome. 3 has 3 towers, 1 has 1 tower, 4 has 2 towers, and 2 has 3 towers. And this looks pretty good, right? And we can see that it's actually better than yellow because, oh wait, I used white, my bad guys. Because yellow tells us that 1 has 2 towers, but we want to decrease the amount of 1s because that block that 1 has can go towards another tower row or column that has more than 1 block. And so because the yellow one has 2 spots, right? 2 blocks over here, but the one and the white only has 1 block, we're going to go with the top view. We're going to go with this view. So I'm going to quickly clear my screen so we can actually start working on the math. Okay, awesome. So now that we know, we should probably look at it from a view like as 2, 4, and 1, and 3. Okay, this is awesome. So now that I know kind of how tall the towers are going to be in this grid, I can just go ahead and solve for it, right? So all the towers in this kind of last column and the 2 column have to have a height of 2. But wait, Corey, it says that we want to maximize the number of cubes we used, right? But why are all the blocks in this column why do all these blocks have a height of 2? Couldn't one have like no heights at all? Or couldn't one just have like 1 block?
That's a great question. Let's see if chat says anything. This is a good question. See if you guys know. So we have these 2 different views. Is there anything that says whether or not we can't have 2 or can't have none? So Stephanie says it's possible, but we're maximizing. That's a great response. So we're looking for the largest numbers of cubes that Irene could have used. And if it's possible for us to place cubes there, we wouldn't want to have no cubes. Because if we could place 0 cubes up to 2 cubes, then if we want to add more cubes inside, we would choose to have all 2 cubes, right? Is that what you were looking for, Gloria?
Yeah, definitely. So the key thing here is maximizing. So it's always really important to read the problem carefully because sometimes questions like these can be easily resolved by the problem. So we're going to go ahead and just find out how many blocks are used in each column. So in the first one, since there are 3 towers and we're maximizing, each of them have 3 blocks. So we do 3 times 3. For the second tower, there's 1 block in 1 tower. So there's just 1 block over there. For the third column, well, there's 2 towers with 4 blocks each. So we're going to do 2 times 4. And for the last one, we have 3 towers with 2 blocks each. And so we're going to do 3 times 2. And so if we add all of that up, we get 9 plus 1. Oops, it's fine. Wait. There we go. That looks like a 1 now. Plus 8. Plus 6. And so adding all of these questions or adding all of these numbers up, we get 10 plus 14 to give us our answer of 24. So what do we think, guys? Do we think that 24 is the right answer? Yes. Okay, this is awesome. Shout out to everyone who did that right. And Albert says 1 plus 6 plus 8 plus 9. And yes, Albert, you are completely correct. And our answer is B. So we'll just go ahead and like check it. Fingers crossed it's right. And it is right. Awesome. Okay, wait. Corey, after all that geometry, are we on a geometry streak? Is our next problem also geometry?
I think our next question is again sort of like geometry. I would say like it doesn't use too many geometry concepts, but we're going to be drawing more squares slash cubes. I think the last question was pretty tricky because it had like a 2-dimensional or even a 3-dimensional square cube because you need to know like the base area and then you need to know how tall it was. But here we just have 1 row of cubes. It says 12, the question reads, 12 colored cubes are arranged in a row. There are 3 blue cubes, 2 yellow cubes, 3 red cubes, and 4 green cubes, but not in that order. There's a yellow cube at one end and a red cube at the other end. The red cubes are all touching, and the green cubes are also all touching. The 10th cube from the left is blue. What color is the 6th cube from the left? Oh my gosh. This is like a word problem about cubes that are in a row, and they give us a lot of information, and they ask us to determine what the sixth cube is from the left. So let's not be panicked from this. Let's not panic from this. I actually think these questions are really fun because we get to sort of build our idea and the understanding of the question one step at a time. And that's exactly what we're going to do. We're going to try and write down our information one step at a time. So first, let me write down my row, and I'm also going to label them because the question says, look, it's such like sixth cube from the left, 10th cube from the left. That means that I'm going to label my locations so that I can have easier access later. 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are my row of 12 cubes. And the question asks us, what is the sixth cube from the left? That's this one right here. And the question also gives us, let's look at this. Let's look at it top down. Like, let's read it from the beginning to the end. I know there's 12 colored cubes, and I already wrote down a row of length 12. So I already used that information. That's a thumbs up. There are 3 blue, 2 yellow, 3 red, and 4 green. Oh my God, that was a mouthful, but let's write that down. So we have 3 blue, 2 yellow, 3 red, and 4 blue. 4 green, sorry. There we go, like that. So this is what I would write down on my paper. And now we know that the next line says, oh, not in that order. Okay, so we need to find out the order they are in. And we know there's a yellow cube at one end. So I'll draw a yellow cube here. And a red cube at the other end. So let's draw a red cube on this side right here. Boom. Now this line is done. Check mark, thumbs up. The red cubes are all touching. Wow, that's actually very important information. Almost as useful. I would say that knowing what cubes are on the end are very useful, but also knowing that all the red ones are touching is also super useful. Because look, we know we have 3 red cubes, but they all have to touch this cube. That means I have to put a red cube over here and also have to put a red cube over here. I can't put them anywhere else, or else they won't be touching the red cubes, right? Because I know that there has to be one at the end. So that's super nice. That line of information gives me a lot of stuff. And now let's look at the next one. The green cubes are all also touching. Wow. So we can do that with the greens as well, but this time we don't know where green is. Let's see, does this color show up? Let's call this color green. And we know there's 4 greens and they have to be next to each other, but I don't know where that is. For example, it could be, let's see, let's make this. It could be over, oop, forgot one of these. There we go. It could be over here, right? Or it could be over here. The sizing is a little bit off. Oops. But you get my idea. Like, we don't know where these 4 green cubes are. And the 10th cube from the left is blue. Wait, is there a problem here? I flipped the sides. Got it. My bad. Good catch, good catch. Whoops. Wait, I got too excited. So this one is the yellow one, my bad. And this one is the red one. Good catch. Thank you, Stephanie. And then these red ones are all touching. Let me make them all the same size. Boom, boom, and boom. Great. So now we know that the 10th cube is a green one. Great, great catch. And we'll ask what the 6th cube from the left is. So that's all of our information on this. Yeah, thank you. Suche also says that 10 is blue. Great. So this is our last piece of information here, and we're done. And now we have to use our math skills. Okay, so the idea here is that, oh wait, sorry, it's blue. My bad. I need a, it's a little hard for me because I have to have the paper on hand, but I'm switching between tabs here. So the 10th cube is blue. Great, blue. And then all the greens are next to each other. Got it. So we have the 4 greens have to be touching each other. And I know that I sort of have this open space right here that I need to put my green cubes into here. Boom, like that. And I can either fit them in, like, for example, I can put them over, let's do the same thing again. We can put them over here. I can put them over here, or I can put them over here. And there's sort of like three ways that I can place them because I can't put them anywhere else. They don't fit, right? They don't fit. They have to be next to each other. There's 4 of them and they don't fit. So the idea is that we can just case break this. So the first case is, okay, I have all my green cubes here, right? And look, the 6th cube is green. Okay, let's note that down. The 6th cube is green. But I can also move all of my cubes. So look at these cubes. I can move them down 1. Boom, like that. If I shift them down 1, the 6th cube, it's still green. Okay, good to know. Now let's shift them down 1 more time. This time it didn't work. Okay. Let's do this 1 more time. And draw cubes. Let's shift them down 1 more. And I'll notice that, okay, the 6th cube is still green. It's completely green. 6 and 7 are completely green. Exactly. Good job. Because no matter where we have this sort of like this wiggle room, it'll only wiggle so much. I can't move it more to the right, and I can't move it more to the left. So the middle is always overlapped with green. No matter where you put your greens, they have to cover the middle because we're sort of fitting 4 squares in the space of 6 squares. There's only 6 squares here that we can fit stuff into. So the middle will always be overlapped. Yeah, and Jerry says, wow, that's nice. I agree, that's really neat. Because we actually don't know what all the squares look like. We don't know where the squares are, but we actually do know that number 6 is green. And that's really cool. And that's sort of like what the question designed too. So we know that it has to be, oh, circle too big. Has to be a green. Let's check our answer. Boom, it's green. Great. So this is sort of another, we use squares in this question. Let's see what the next question is. Are there squares in this one, Gloria?
Unfortunately, not this time. We've broken our geometry or geometry-ish streak. Now we're moving on to just pure numbers and some variables. So the problem says, how many 4-digit numbers A are there such that half of the number A is divisible by 2? A third of A is divisible by 3, and a fifth of A is divisible by 5. Okay, so let's kind of write down all the info that we have. We know that half of A, or A over 2, is divisible by 2. Half of A is divisible by 3, so A over 3 gives us 3. And a fifth of A is divisible by 5. So A over 5 must, be divisible by 5. Well, right away we know that, hold on, let's just think for a second. If A is odd, it can't be divisible by 2. So A over 2 cannot possibly be divisible by 2. So therefore, A must be even at least, right? So we know that A must be even. But, if A was just divisible by 2 and nothing like 4 or 8, well, then A over 2 can't be divisible by 2, right? Because A over 2 is divisible by 2. This means that A itself must be divisible by 4. Right, so 4 is a factor. And same thing here, right? Well, if A over 3 is equal to 3, or not equal to 3, but is divisible by 3, well, A itself must be divisible by 9. So we know 9 is a factor. And same logic here, if A over 5, or a fifth of A is divisible by 5, well, A must be divisible by 25. And you might be wondering, where am I getting all these numbers from? Well, I'm just getting them because while this isn't like an exact equation, right? I'm just getting them by multiplying the denominator and the numbers themselves. So for this one, we get 5 squared is equal to 12, or 25. I don't know where I got 12 from. 3 squared is equal to 9. And then on the top is 2 squared is equal to 4. Okay, so we know that 4 is a factor, 9 is a factor, and 25 is a factor. Well, if all 3 of those numbers are factors, then 4 times 9 times 25, is that also a factor, right? Yeah, Stephanie, you put it really awesome. 4 is divisible by A, or 4 is a factor of A, 9 is a factor of A, and 25 is a factor of A. And so, yeah, because all 3 of those numbers are factors of A, you think that their product must also be a factor of A, right? And Stephanie says yes. Yeah, you guys are absolutely correct. And we can see with some quick multiplication that 4 times 9 times 25 is equal to 9 times 100 to get 900. So now all we're really trying to find is a number of 4-digit numbers that are divisible by 90 or have 90 as a factor. So let's just go ahead and just list some multiples of 90 or 900. 900, 1,800, 2,700, 3,600, 4,500, yada, 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 all the way to 7,200 to 9,000. Yeah, okay. And oh, wait, hold on. Not 9,000. I skipped a number there. To 8,100 or 81,000, then to 9,000, and then can you guys still see? Okay, awesome, you can still see it. Yeah, awesome. Okay, so looks like, yeah, okay, wait, I think Stephanie listed them in there. Okay, I'm not going to read that out because it's really, really long, but Stephanie listed all of them out, which is super duper awesome. And you may be wondering, wait, why are we stopping at, 9,900? Can't we just add on another 900? Well, the thing is, if we add on another 900, it's not going to be a 4-digit number anymore. It's going to be a 5-digit number, and that exceeds our limit, right? Our question specifically asks for 4-digit numbers. And so within the 4-digit range, we must stay. Okay, so now something interesting that you might note is this is 1 times 900, 2 times 900, 3 times 900, and so on, all the way to 10 times 900 and 11 times 900. And so, hey, Corey, since it goes all the way up to 11 times 900, which is 9,900, 11 must be our answer. Am I correct? What do you guys think?
I think we're a little bit off. Can anybody see where the problem is? I see that Suchai has already said the correct response in chat. So the question reads, how many 4-digit numbers A? Does anybody see any problem here? We have 11 numbers in our list, but is the answer going to be 11? What should the answer be? Exactly, it should be 10 because we have 11 sort of like answer choices that we got to, but we'll realize that the first number 900 isn't actually a 4-digit number, so we shouldn't have 11 4-digit numbers. We'll only have 10, and that's where the answer is going to be D10. Now, Gloria, you want to do the question review?
Yes. Okay. So our answer is 10. So let's go ahead and see if the answer of 10 is correct. And voila, it is correct. Okay, awesome. So I think we've gone a bit over time. It's now 7:03. So so that's it. That's all the questions for today. So thank you guys so much for coming. Yeah, it's been awesome with you guys.
Thank you, thank you. And I know I had a little bit of some technical difficulties earlier, which kind of took up some time. So I know you guys are all free to leave now because we're past time, but I'm gonna try and see if I can explain the next question too, really briefly. If you guys want, if you're curious to stay, because of some issues earlier, I've kind of wasted some time. So I'd be down to explain this question, and I think it's really fun. So if you guys are willing to stay, you guys can stay if you guys are curious about this question. But if not, you guys are free to leave. Thank you so much. Thank you, guys. Thank you for attending the live solve. Bye-bye. Thank you, Erica. Alrighty, so now, although the live solve is over, there was some weird glitch earlier. Let's take a look at this question, and we'll use this as like a redemption question. And it's actually a very difficult question, but I won't go too deep, too much in depth into it because there's not that much time left. But the question says that, I'll just summarize the question. It says that we have this square here. And it's nothing actually about a square, even though it looks like more geometry. The idea is that I place numbers here. And on the sides, And then I'll multiply these two together to get a number in the corner. And I'll multiply these two together to get a number in the corner. I'll multiply these two together to get a number in the corner. I'll multiply these two together to get a number in the corner. And now these corner numbers are sort of like the product of all the side numbers. And then if I add up all of these corners, they add up to 15. And it's asking us, okay, we need to find out what the sort of edge numbers add up to as well. So this question is very, very interesting. What we know is that they add up to 15. Now, immediately what we can see is that, wow, 15 is actually very, very small. 15 is very small. For example, if I put like in the number 10 here, and then put the number 2 here, immediately we have 2 and 10 multiplied up to 20. And the question also says that we have to have positive integers, so there's no negative numbers. If I have a 10 here and I put a 2 here, immediately I already have 20. That's too big. That's bigger than 15. I have to add up all the corners and they add up all to 15. So we can't have too big of a number. And if we think about it, another thing we can think about is, okay, let's say I have the smallest possible combination, 1, 1, 1, 1. This will add up to 1 in this corner, 1 in that corner, 1 in this corner, 1 in that corner. They'll add up to 4. They'll add up to 4. But wait a second. What do we notice about 4? 4 is even. 4 is even, and our answer is actually odd. So we can sort of work off of this very small 1, 1, 1, 1 case to realize that parity of the answer matters a lot. If they're all odd numbers on the sides, if they're all odd, then this corner will be an odd times an odd. That'll be odd. That'll be odd. That'll be odd. That'll be odd. 4 odd numbers are actually, they add up to an even number. So we can't have all odd numbers. So they cannot be all odd. Okay, that gives us some information. And the same thing happens in reverse. So if they're all even, then the sum is going to be even. So it can't be all even either. And if I have 3 even numbers, for example, 2, 2, 2, well, even if this, let me see, that's a little bit unclear. So let's make a new slide. If I have even here, and then let's just copy paste. Boom. If I have an even number here, and an even number here, and an even number here, if I have 3 even numbers, then it doesn't matter. This corner is going to be something times an even number, so it's going to be even. And this corner is going to be something times an even number. It's also going to be even. So I can't have 3 even numbers. I can either have 2 even numbers or 1 even number. So let's see. If I have just 1 even number and the rest are odd, let's test this out. Okay, so this is going to be even. This is going to be even. This is going to be odd. And that's going to be odd. But if I add up even, even, odd, odd, that adds up to an even number. So I can't have that either. So we can have, so there's 4 numbers, right? On the sides, 4 sides. There's even and odd, right? Let's make up a tally, like a little table. If I have no even numbers and 4 odd numbers, that does not work. If I have 1, 3, or I can have 2 and 2, or I can have 3 and 1, or I can have 4 and 0. But we know that this one also doesn't work. We just showed that this one doesn't work. And we know that 3 and 1 also doesn't work because we showed that as well. So it means that we have to have 2 even numbers and 2 odd numbers. Good to know. And now we start testing. So I don't want to ramble on too much, but we know that it can't be too big because they have to add up to 15. The numbers can't be too big. On average, right, there's 4 corners. So if we divide by 4, it'll be on average like 3.75. So on average, the corners have to be 3.75. So we kind of guess that there should be a 3 here. Okay, if there's a 3 here, I can either have like 1s here, or I can have 2s here, or I can have 3s here, right? But let's say we have 2 1s. Oh, wait, I can't have 2 1s. I have to have 1 1 and 1 2 because I can only have two odd numbers and 2 even numbers, right? So let's just test this case out. This would be the first case that I test. 3, 1, and 2. And then I would get, okay, so this adds up to a 3. That adds up to a 6. So in total, our sum right now is 3 here, 6 there. It adds up to 9. And we want our sum to tally up to 15. That means we're missing 6 more. That means that these two numbers should add up to 6. Let's make this yellow. These two yellow numbers needs to tally up to 6. But look, we already have a side length of 1 here and a side length of 2 here. So let's just test it out. If I put the number 1 here, then it's 1 times 1. Let me see, I can't see my own screen that well. It's 1 times 1 and 1 times 2, that adds up to 3. But if you notice, if I just put a 2 here, then I'll have 1 times 2 and a 2 times 2, and that adds to 6. So we find out that the answer is going to be 1, 3, 2, and 2. And if you notice that we have two odd numbers and 2 even numbers, exactly what we showed. And this is the way to test it out. Like, you just pick a number, throw a 3 up here, then we guess what the other 2 are, and we just work it up. And we'll notice that, let's say we don't get so lucky, we don't guess on the first try. Well, this 3 case fits perfectly. If we were to guess 1, then we'll be like, wow, 1, it's a little bit too small. So we're going to work with other numbers, and eventually we'll find the right case. And the answer is 1, 3, 2, 2. So if we add them up, what do we get here? The question asks for the sum of the edges. So 1, 3, 2, 2, that adds up to 8. So it should be C8. And that's going to be our answer. Let's see the answer. Boom, great. All right, thank you guys. Sorry for the little bit of a technological error earlier, but I wanted to finish a super cool question. Wow, it looks like Andrew has a really long solution. So thank you guys for staying, for those of you who stayed. But you guys are all definitely super free to go now. So thank you guys. Thank you all of you guys. Bye-bye.
Yes, thank you guys for coming. It was awesome
Thank
having
you.
you guys today. All right, bye guys. Yeah,
Bye
bye
guys.
Rika.
Bye-bye. Thank you.
Bye Sanskriti.
Bye everybody.
Bye guys. Bye
Bye,
Stephanie.
thank you. See you in the future. I hope you
Yes,
guys keep
hopefully we
doing
see
this.
you guys.
Yep. Bye-bye.